Hello, and welcome to Unit 2. This is going to be discovering the night sky. If you've noticed that my background's a little different, I had the floors done downstairs and we had to move all the furniture, and my wife didn't like the setup of my office, and I guess I didn't really like it much either, so we have it oriented. So if my desk used to be at 12 o'clock position, it's now at the 3 o'clock position. And behind me I have my empty CD rack. I'm contemplating getting rid of my 600 plus CDs, which I don't listen to much anymore. Just not sure what I want to do with them yet. Don't know which ones I want to keep. If I want to get rid of the whole catalog, I'm not sure what I'm going to do, but that's neither here nor there. Okay, so let's go into Unit 2. Unit 2, this is going to be 2A. I'm actually going to show you what the 2A, 2B, C, and D are. First one's going to be constellations. I think it's about 14 slides. Then we're going to go into B, talking about sky domes and celestial sphere. And at this point, I hope I actually have a different computer up there for the LCD, one that I can actually download a program called Celestia and get it to run correctly. Right now, you open it up and it just crashes. And I've had a problem with that for a couple of years, but since I wasn't teaching earth science or astronomy, it wasn't a problem. But now I'd really like to be able to get it, and I'll explain more about that program later. C is going to be movements of the Earth. D is going to be moon phases, and it's also going to be when the moon phases are lined up, and we actually get a disappearance of the sun or the moon called the eclipse. So what do we think? Is the North Star, Polaris, the brightest star in the north sky, in the night sky, sorry? Do astronomers regard constellations as familiar patterns of stars in the sky? What causes seasons? When is the Earth closest to the Sun? How many zodiac constellations are there? And if they're not zodiac, what the heck they're called, and how many would those be? Does the moon have a dark side that we never see from Earth? And is the moon ever visible during the daytime? So we will discover how astronomers organize the night sky to help them locate objects, like a map, to the Earth, that the Earth's spin is on its axis and it causes both day and night. Half the Earth, 50%, is lit up at the daytime at all times, and half of it is night. And it all depends on how much of that day you get or how much of that night. And believe me, if the day gets longer, nights get shorter. When it's not always 24 hours of each, but 50% of the Earth is always facing the sun and 50% is always facing away. How does the tilt of the Earth's axis of rotation actually affect our seasons? What's the moon's orbit around the Earth, and how does it create phases? And how does it actually create lunar and solar eclipses? How is the year defined, and how is the calendar developed? I don't really remember that in this PowerPoint. The universe is huge, and sizes and distances of this universe vary greatly. We understand inches pretty well, we understand feet pretty well, miles we have a pretty good understanding as long as we don't get too large. But when we start talking about the solar system, we need to talk about millions, billions, trillions, quadrillions, quintillions, even larger units. And sometimes those numbers get so big that we don't have a compensation for it. You guys can imagine 10 Twinkies, you can imagine 100 Twinkies, 1,000 Twinkies. Would a million Twinkies fill that classroom, floor to ceiling, wall to wall? Would it take a billion Twinkies? And if it actually filled more than the room, how far would it go down the hallway, and how many other rooms would it fill? So, some of the common examples of scientific notation, that units of 10 that we actually use to describe numbers that are much smaller and much larger than 1 to make it easier for us to understand, because this creates a number between basically 0 and 10. We understand those, except the unit may be a little hard to understand. So some of the common examples of the power of 10. We have 10 to the negative 6, which is a millionth. I'd like you to understand that 10 to the 6 is a million, so negative 6 is a millionth. It's also called a micro. 10 to the 3 is always 1,000. 10 to the 9 is always a billion. 10 to the 12 is always a trillion, and you should know those easily. And do you know what 15 would be? What's bigger than a 2, a 3? How would you say a 4-illion, a quadrillion? And micro, kilo, giga, and tera. You may actually get these units because of computers. Anybody know what the next one is? Once our terabytes get to be 1,000 terabytes, or we may even get it closer when we say half of a, well, you'll see that here. So kilo, mega, giga, tera, it's going to be a petabyte. So when we get to 500 terabytes, we may actually call them a half petabyte drives. And then we're going to keep going to larger and larger drives as our processes go on. You know, my very first computer used 5¼ inch floppies, 512 kilobytes, and then we actually came up with a harder floppy disk, 3½ inch disk, and that actually got into megs, and then we got into gigs, and now we're into teras, and probably before we got to gigs, people didn't know what was bigger than a megabyte, but now we know. Here's the size of them, and this one goes even a little bigger, because this over here actually ends up with Yoda, but we can go to Bronto and geobyte. Okay, so scales of the universe. We start from the very small. The range of objects actually go from things smaller than the units of a proton, and we will talk about those, I think, a little bit when we talk about the forces of nature. And each of these actually go up by 100,000, or they go up by 10 to the 5th. That should be 5th, not 6th, and I didn't catch that. So -5th, then we go to 1, and then we go 100,000 times bigger than that, and 100,000 times bigger than that. You can see we're already at the diameter of the sun. And then we go to distance from Earth to the sun, and we can go to distance of nearby stars, and distance of the galaxy, and size of the observable universe on the same scale as things that are smaller than subatomic particles. But that's because each of these gets 100,000 times bigger. Okay, I'm going to show you this site, and I actually have 2 monitors here, so I've got to come over here and get this, and then drag it over here. What language would you like to see it? I'm going to try English, British. Okay, we have a scroll bar. Click on the objects to learn more. Let's go ahead and start. I said let's go ahead. There we go. And what they're going to do is they're going to show you common objects. They're going to talk about them being reference to a circle. This is a 1 meter circle. The Earth ball, which was in the classroom, it still could be in the classroom, but was in the classroom at some point, is a 1 meter Earth ball. That thing that's hanging over the table over by our door of our classroom. You can see giant earthworms, bigger than a meter. Basketballs, smaller than a meter. Large hailstone, smaller. Can you make out what that is? If I just scroll in a little bit, that's a hummingbird. Matchstick pennies, we can go a lot smaller than that. This is the approximate size of this viewpoint, so the screen that we're looking at. Now you got dodo birds and beach balls, and now you have humans. Throw in a T-Rex, throw in the Apollo lunar module, giraffes, elephants. Looks like we have an average U.S. home. Largest critter that's ever been on the planet, wise. Redwood tree, one of the largest creatures. Boeing 747, when we go out to 1,000 meters, start seeing mountain ranges, start seeing comets, moons of planets, Demon, Mars, Halley's Comet. Then we have a marathon, 26 miles, got the smallest state. Throw in some other astronomical things, throw in some states, and we have a 1,000,000 meter circle. Planets, and that's a gigameter, so this is a billion meters. Now we're throwing in some stars, the sun being one of those. Where was the Earth? Way over there. How many of those would it take to go across here? We're going to say it's more than 100. It's about 108. This is the biggest star in our sky. This is a very changing star. When we go to largest star, there's Polaris, Aldebaran, Rigel. Some of these stars you'll get to learn later on. Now we're out to a billion, trillion. I gotta get this. There's a million. There's a billion. This is a trillion. And we're going out to larger stars, some of which you can see. You can see Antares. This is the largest, one of the largest stars. Here's the solar system. Neptune to the sun. Put a Neptune out there, and if I take that star and stick it in the middle, the Earth is well within there. There's the Kuiper Belt, which is the thing that's outside of Neptune's orbit. And we have nebula. There's a light day. The distance light travels at 186,000 miles. There's the distance for Hale-Bopp, which is a comet. It's farthest away from the sun. Now we go to a quadrillion meters, and we start throwing in nebula. And we go to millions, billions, trillions, quad, quin, septillions. And now we're talking about larger nebula. Go at 1,000 times larger. And 1,000 times larger than that. And there's the observable universe. And what lies out later, we don't know. And then we can also go all the way back in, all the way back into a little farther than I wanted. There's the hydrogen atom, the helium atom, and then gamma rays, and then we go to subatomic particles, and then we go to even subatomic particles, and we get to the smallest unit that they're going to use, which is part of the string theory, the Planck length for a constant, and then start talking about quantum foam, where we start bending time. So, kind of a cool site, and you can access it from the PowerPoint, which I will try to put up on our website, part by part. Okay, constellations. These are a group of stars that form a pattern. Usually these patterns were given by the ancient people. That's why they've got such cool names and cool stories. In order to more easily locate objects, astronomers now use these patterns, these constellations, as a road map, like states. So this is what the ancient constellation looked like. This is Orion the hunter. He had a bow. He actually has got arrows or spears up in this area. He's trying to hold off. This is Taurus the bull, the horns and the head of the bull. You can see we have Gemini, which you can't see much of. The dog, two dogs. There's Canis Major, which has the brightest star Sirius. That's a really cool star called Betelgeuse or Betelgeuse, the way it's real pronounced, but we call it Betelgeuse. And there's Rigel, two really big, easy stars. There's the belt of Orion, and we'll talk about that as not being really a constellation. It's part of a constellation, but people actually talk about it as being its own thing. Here are the 88 official constellations that make up everything in our celestial sphere. So if we actually see a comet in this part of the sky, we call it in Hercules, or we call it in Cygnus, or Cepheus, or we talk about it in Hydra, or it's up here in Virgo, and a lot of things in the constellations of the zodiac. And you can see Leo is there, and Cancer is there, Gemini is there, Virgo. And where's the next one? I see Pisces. Actually, that's Draco. I don't see where the rest of them go. They've got to be on here. But anyway, these are the constellations that make up the 88 sections of the night sky. Okay, angular distances, celestial objects. You can see you can hold up your hand, and if you hold your hand up at arm's length, if you look at that index finger, that's about 1 degree, and that means I can put 360 of those things all the way around the circle, all the way around, all the way back. If you actually hold your hand out, this is about 10 degrees. Go like this, we've got 3, 4, and 6 degrees. If you look down here at the bottom picture, this is supposed to be the same size as that, and I kind of disagree, but it's about the same, the right size. Hold up 3 fingers, you get 5. There's your 10. There's your 15, and there's your 25. So if you did that, 10 of those, that'd be 250 degrees all the way around. Okay, a neat thing to think about, that 1 degree right there. Here's the moon. Moon is 250,000 miles away. It's really a pretty good sized rock. But in our sky, it only has a distance of about 31 arc minutes. 1 degree is equal to 60 arc minutes. Where do we see that degree again? Oh yeah, right there. So that moon, which is 1/2 of a degree, would fit halfway across this finger, and you can get another moon. In other words, you could get 2 moons, and if you look at this picture, moon and the sun, 400 times farther away, but 400 times bigger. If you actually take a look at these, they actually have the same, almost the same apparent size. So 2 moons or 2 suns would fit across there. So if you hold your finger up like this, close one eye, and if I did that, I could cover up the sun twice. Pretty cool. Okay, there's our bear. I would like you to draw your rendition of these hand sizes for the celestial sphere. Some common guides that you can find in constellations. This is Ursa Major. It's the big bear. I think our paper is named after this. Our Bruin, we can almost use this as our mascot. But one important thing you have to understand when you start talking about the Big Dipper, which is this group of 7 stars, the tail and the back hip of the bear, this is called an asterism. Just like any other part, and we'll talk a lot about these. Big Dipper is not a constellation. It's part of Ursa Major. Some of the asterisms we actually talk about are parts of more than one constellation, like the summer or the winter triangles, some other ones, but they're not part of those 88. So what can we use the Big Dipper to find? The easiest thing is to find Polaris, the North Star. The neat thing about the North Star is not the brightest thing. If you take a look at Hubble, the Hale telescope, the 4-meter telescope, the 1-meter telescope, as we go down we see less and less. With binoculars you can't see as much as the telescopes, but you can see Barnard's star with that. Naked eyes are about here, and then there's Polaris, and there's Betelgeuse, and we go to Venus, the brightest thing next to the full moon or the sun in our sky. So actually the things get brighter apparently as they go this direction. So is Polaris the brightest thing in our sky? No. So don't go out and find the brightest thing and say it's Polaris. Polaris, once you find Polaris, I can walk out of my door and I can look at those two, or I can actually don't have to look at those 2 stars anymore, because the neat thing about these is these orbit around that star. That's the pole star. It's what's actually sitting right over the North Pole. If you were standing at the North Pole like Santa Claus and looked straight up, that Polaris would be above your head, and it would always be there. Just like it's always, if I walk out my door and I point to the left up around 38 degrees high, I can actually look at my finger and it's actually pointing at Polaris. Okay, you can use those 2 stars right there in the Big Dipper to find that star. It's the only, in a really dark sky there are more stars there, but it's really the first easy star to see with your eye, and it's about 5 of those distances away. You can use these 2 to actually find Regulus, part of Leo. You can use this handle of the Big Dipper, arc to Arcturus, and then you can arc even more to Spica, which is part of Virgo constellation. So you can use the Big Dipper to help you find the constellation. It's really a relatively easy, 7 relatively easy stars to find. I don't know if you can see them in New York City, but you can see them even in bright locations. And there's a picture that has some artistic ability, and you can see here's the Big Dipper. Use those 2 stars to find Polaris. You can arc over to Arcturus, which is part of Bootes. You can see Hercules is up there, Cygnus the swan is up there, Draco the dragon. There's the little bear, which is Polaris, is the tail star of Ursa Minor. We have Cepheus and Cassiopeia. We have Perseus with Medusa's head. We have Auriga the charioteer. We have, this is Andromeda, who Perseus is actually saving from Medusa. But really cool stories with some really cool creatures. Here's a listing of the common names and distances of 20 of the, and actually I think that's 20, 2, 4, 6, 8, 10, maybe a little more than 20 of the brightest stars in our sky. And if you notice, we start talking about Sirius, or we start talking about Altair, or we talk about Antares as being alpha stars. These are the brightest stars in the constellation. Beta are the second brightest. Although I think they have this thing off a little bit because we actually have Beta. We have Rigel, Beta, being brighter than, where's the, down here by Betelgeuse, which is Alpha star in Orion. But if you take a look at it, we'll talk about apparent and absolute magnitudes. Apparent magnitudes are from the Earth, and you can see Sun is the largest negative, which is the apparent largest. The negative stars are brighter than the positive stars, and we'll talk about how we figure that out later on. Absolute is looking at a distance from 26 light years away. So if we actually got 26 light years away from the Sun being really bright from the Earth, get farther away, the number's not going to be as bright. If you look at some of them, like this star must be farther away, and it looks like it's 74. So if you got one arc second away from it, you can actually get closer to it, so it would get brighter. This one got dimmer, this one got dimmer, that one got, and the more positive they get, the more negative this one would really get bigger. This is actually one of the two biggest, brightest stars you can see with your eyes. Deneb down here is the second one. So if you take a look at its distance, it's really far away. It's still fairly decently bright, and if we got closer to it, it would get brighter. But this is a list of the relatively bright stars apparently, and as the numbers get larger, the brightness gets smaller. There's the summer triangle. Actually, I was at Wolf Trap last night watching a concert, and I got to see this. Deneb being the brightest star in Cygnus the Swan, Vega actually being the brightest star in Lyra the Scales, and we have Altair, the brightest star of Aquila the Eagle, and the eagle supposedly is actually flying towards the neck of this goose. It looks like a summer cross inside the summer triangle, but it really is a goose. Sorry, a swan, long-necked, both of them. This arrow, this eagle is going off towards it. This thing is supposedly flying to the south. If there's east, south is over there. The winter triangle, not as easy to see as the summer triangle. A lot of big stars out here, so you may get confused. But if you use Betelgeuse or Betelgeuse, Rigel's a pretty bright star. This is Sirius, the brightest star next to the sun in our sky. Because it's fairly close. This is bright because it's really big, and that's as bright because it's even bigger. That's a blue giant, this is a red giant, this is a white. I'm really not sure what the nomenclature for Sirius is, but we have orange stars, and we have reddish colored stars, and we have blue stars, and we have white stars. And this is actually looking towards the south, and this would actually be winter, so we got to wait a few more months to get this one on our sky. Or if you're up at 3 o'clock in the morning, I'm sure it's probably there too. You can also use the belt of Orion to find Aldebaran, part of Taurus the Bull. Can't really see much of Taurus. You can use this one going down towards Sirius. You can see that. You can use these two going over to Procyon, which is actually making the triangle. So you can use constellations to help you find other constellations. And if you can find Orion, you can find a lot of the critters that are around it, and a lot of the people, the twins, and other things, the bull and the rabbit and other things. They got a big dog and a little dog, hunting dog for the hunter, which is cool. And there's our stop. So thanks for stopping by, and that is the end of 2A. Bye.